one of the best examples of the use of separation of variables is for the logistic growth model. So previously we looked at simple exponential growth, where say P of t is the population of a bacteria at time t, and we assume that the growth rate is proportional to the current population. So a model for that could be dp dt is equal to a times p, because the growth rate is a constant times the current population. And then p of 0 is p sub 0. Now we know what the solution to this equation is. It is p0 e to the at. And what we have here is exponential growth. And in particular, as t goes to infinity, the bacteria population increases at an exponential rate, so the bacteria population explodes. It just continues to grow and grow and grow with no limitation. But we know that this is not the case. Otherwise, bacteria would be filling every room. So what if the population growth is limited by the amount of resources that are available to the bacteria? How can we model this behavior? So what I would like you to consider is a model that looks a little bit like the exponential growth model, but also adds some sort of limitation. So we're going to let dp dt equal a times p. And then we're going to limit the growth by adding another term, 1 minus p over k. And again, the initial population p of 0 is going to be p sub 0. So we're going to say that essentially that the growth of the population is proportional to p, but it's also proportional to this term 1 minus p over k. Let's see what the effect is. What happens when p is small? Well, if p is small, then p over k is going to be even smaller. And so 1 minus a small number is going to be close to 1. So this term here, when p is small, is going to be close to 1. In that case, what we have is that dp dt is going to be approximately equal to a times p. And so when p is small, we are going to have exponential growth. So there really is no change in that case. But what happens as p gets closer to k? Well, then this term here, 1 minus p over k, as p gets closer to k, then p over k is close to 1, and so that term is going to get close to 0. So as p gets closer to k, we have that dp dt ends up being approximately 0. So we have little to no change in the population. And so now you can see that there's some sort of limitation to the growth of, say, this bacteria colony. And then what happens when p is larger than k? Well, if p is larger than k, again, this term ends up being negative. And so if p is larger than k, then we have that dp dt is negative. So in that case, the population is going to decay. And so this logistic growth model is going to limit the growth. To really understand what's going on with this model, we should look at a slope field to see to see exactly what's going on. So let's check out this slope field with the growth rate A being 0.1 and then this new constant K being 20. Let's check that out in slopes. So what I have is a logistic growth model. And what I'm going to do is I'm going to start off with a small population, say a population of 1. Well, initially you'll see that this curve is growing exponentially, but as we get closer and closer to 20, we see that the growth seems to taper off. In fact, we can see as we get closer and closer to 20 that it stops growing. All right, so solutions that start small start with exponential growth, but that growth eventually gets limited. Okay, if we start above 20, we see that the population decays, and it seems to decay back down to 20. And so with this logistic growth model, there seems to be a limit to that growth, and that limit seems to be 20. Okay, so I can fill in a few of these solutions. Let's think about the equilibrium solutions, because it's always nice to put those in. Okay, if we're looking at dp dt is equal to, say, a times p times 1 minus p over k, and we want to set that equal to 0, we notice there's two equilibrium solutions, p of t equals 0 and p of t equals k. So if the population starts at 0, well, then there can be no reproduction, so it remains at 0 for all time. This was true of the exponential growth model. But now, if the population starts at k, in this case k is 20, notice that it has that horizontal slopes, and so if the population starts at k, it remains at k. And then, if you start with a small population, it will grow up to 20, and if you start with a larger population, it'll decay down to 20. So 20 seems to be kind of the limit for this population. Okay, so k is the limit for this population. And so what's the significance of this quantity? Well, it's some sort of limiting value for the population. And in biology and ecology, we call that a carrying capacity for the population. So the significance is, with this carrying capacity, we're assuming that there's a limited amount of resources for the population to grow, and that the population in this case cannot go above k because the resources will not allow the population to go above that carrying capacity k. Okay, so I want to finish by solving the logistic equation. So we're going to try to solve the logistic equation, and we're going to solve it with these two constants. A is 0.1, that's the growth rate, and then the carrying capacity K is going to be 20. So here we have dp dt is equal to 0.1 times p times 1 minus p over 20. And you can see that this is actually a separable differential equation because everything on the right-hand side only depends on p. So I can have all the p's on one side, dp over p times 1 minus p over 20 is equal to 0.1 dt. So now I just have to anti-differentiate both sides. But first, before I do that, I'm going to go ahead and multiply both sides by 1 over 20, because I think that's actually going to help me in solving this problem. So that instead I have dp over, let's see, so I'm going to have p times 20 minus p, and then that's going to equal 0.1 over 20 dt. Okay, so how do I compute this antiderivative? Well, what I'm going to have to do is use the technique of partial fractions. Okay, so I'm going to rewrite dp over 20 minus p times p as a over p plus b over 20 minus p. Okay, so that means if I was combining these two fractions, I would have to multiply this fraction by p over p, and then I would have to multiply the first fraction by 20 minus p over 20 minus p. So essentially I get a times 20 minus p plus b times p is going to equal 1 plus 0p. So combining the p's, I'm going to get that minus a plus b has to equal 0. That tells me, of course, that a equals b. And I get that minus a times p is going to equal 1. Sorry, minus a is equal to 1. Looking at, sorry. Let's do that better. 20 times a is going to equal 1. So these are the terms with p, and these are the terms with 1. So that tells me that a is equal to 1/20. So it turns out that dp over p times 20 minus p is going to equal 1 over 20 times a over p plus 1 over 20 times, that a is actually a 1, sorry, 1 over 20 times 1 over p plus 1 over 20 times 1 over 20 minus p. Okay, so we're going to bring this back over here, and we're going to have, let's see, 1/20 times 1 over p plus 1 over 20 times 1 over 20 minus p is equal to 0.1 over 20 dt. Aha, now you can kind of see why I was doing this, because the 1 over 20s appear in each term, and so they cancel out. So I'm going to get 1 over p plus 1 over 20 minus p. Okay, both of those have a dp on them, is equal to 0.1 dt. Okay, so now I'm going to anti-differentiate both sides. So I'm going to get the natural log of p, and then it's going to be minus the natural log of the absolute value of 20 minus p. Very important that I include the absolute values there. That's going to equal 0.1 t plus the constant c. Now we can use natural log rules to combine this. So we're going to get the natural log of p over 20 minus p is equal to 0.1t plus c. So remembering that the natural log of the quotient of p and over 20 minus p is the natural log of p minus the natural log of 20 minus p. Okay, so it's at this point when c is almost isolated that I'm going to want to solve for c using the initial condition. So here I'm going to use the initial condition. I'm going to move this down real quick so everything kind of lines up nicely. Okay, the initial condition, okay, says that the natural log of p0 over 20 minus p0 is equal to, okay, 0.1 times 0, so that ends up equaling c. And in this case, I'm not going to substitute in for c in this calculation yet. I'm going to tell you what c is, and then I will substitute in for what c is at the very, very end of this calculation. Okay, so just remember that we solve for what c is. Okay, so now I need to solve for p. So I need to do e to both sides. So I get that the absolute value of p over 20 minus p is equal to e to the 0.1t plus c, making sure that that plus c, of course, is in the exponent. Another way to write that is e to the 0.1t times e to the c. And so this becomes, okay, this becomes e to the c, so this becomes the natural log of p0, sorry, e to the c is actually just going to be p0 over 20 minus p0 times e to the 0.1t. So I'm going to substitute in for c there. Now, it's going to get awkward to keep carrying around this, this term here, p0 over 20 minus p0. So I'm going to go ahead and give that a name. We're going to call that d. So d is going to equal p0 over 20 minus p0. Okay, so what we have is essentially that the absolute value of p over 20 minus p is equal to d e to the 0.1 t. Okay, so at this point, we have to ask ourselves, when we drop the absolute values, is this going to be a plus or a minus? Okay, so we want to look at a specific case for the moment. Okay, so the specific case that I want to look at is, I want to say, we're going to assume that p is between 0 and 20. Now, we can make these kinds of assumptions that p is going to be between 0 and 20. We could have also considered a negative p, or we could have considered a p that was bigger than 20. I'm just going to solve in this case, and then you would have to do something similar in the other cases. Okay? In that case, we're going to end up with a positive. So we're going to end up with that p over 20 minus p is going to equal d e to the 0.1 t. So that tells us that p is equal to 20 minus p d e to the 0.1 t. And that's going to tell us, let's see, that p plus p times d e to the 0.1 t is going to equal 20 d e to the 0.1 t. Factoring out p, we have p times 1 plus d e to the 0.1 t is going to equal 20d e to the 0.1 t. So p of t, finally, is going to be 20 times d e to the 0.1 t over 1 plus d e to the 0.1 t. And that is the solution, and we could plug in what d is, but it's not very illuminating. So we're going to have to do just a little bit more work. So I'm going to multiply top and bottom by 1 over d. And I'm also going to multiply top and bottom by e to the negative 0.1 t. Okay, so what is the result for that? Okay, so p of t is going to equal, let's see, 20 over, because that's going to eliminate the d and the exponential on the top. So 20 over 1 over d e to the negative 0.1 t plus 1. Okay, so let's see if I can write that another way. So p of t is going to equal 20 over, let's see, 1 plus 1 over d. Well, oftentimes they just say that's 1 plus some sort of constant. Let's call the constant c, for lack of a better term there. Okay, and so it's 1 plus a constant e to the negative 0.1 t. Now, what is that constant in particular? Okay, what is that 1 over d? So 20 over, let's see, 1 plus, let's see, 20 minus p0 over p0. That's going to be 1 over d, e to the negative 0.1 t. And I could include the absolute values there, but I don't need to because I'm assuming that p is between 0 and 20. Okay, and that is what is called a logistic curve. Okay, so we'll note that p of t is always going to be positive as long as I'm starting between 0 and 20. Okay, but what's important here to note is it has that characteristic that as t goes to infinity, that exponential decays to 0, and so p of t goes to 20, which is our carrying capacity. So we have evidence here from this formula for the logistic curve that as t goes to infinity, our population approaches the carrying capacity. Now, you should probably have a general formula for the solution to the logistic equation in your textbook, and you might want to use that when solving, because as you see, this was a long problem to solve. And this is why I often say it's not fun to solve problems using separation of variables, because if a problem requires separation of variables, if a model requires separation of variables to solve, then the amount of work that you have to go through to solve that problem is often quite significant. And the simple problems, like the examples that I showed you earlier, they only come up as toy problems. Okay, the ones that relate to physical models, those problems tend to be more difficult to solve. So that's why solving problems using separation of variables often is difficult when you're looking for something that has a physical representation, a true meaning.